Hi everyone, and welcome to this educational video. My name is Dr. Hendy. In this video, I am excited to be here with you today to talk about general information on thermodynamics. In this presentation, I will be discussing 1. Fundamental properties of state functions. 2. Definition of thermodynamic systems and the external environment. 3. Description of a thermodynamic system. 4. Ideal gases. 5. State of thermodynamic equilibrium of a system. 6. Possible transfers between the system and the external environment. 7. Transformations of the state of a system, operation, evolution. 8. Reminders of the ideal gas laws. 9. Energy exchanges of a system, heat or amount of heat, work of pressure forces. So, without further ado, let's get started. Thermodynamics. The goal was to study the transformation of heat into energy. Thermodynamics. Heat movement. Definition of thermodynamic systems. Thermodynamics comes from the Greek thermos and dynamis, which means heat and energy. It provides general and effective methods for studying and understanding complex physical and chemical phenomena. Thermodynamics is concerned only with the macroscopic properties of matter such as pressure, temperature, volume and composition. System and external environment. A thermodynamic system is the part of the universe that we want to study. Everything that is not part of the system constitutes the external environment. Universe equals system plus exterior. Homogeneous system and heterogeneous system. The homogeneous system is made up of a single phase, gas, liquid or solid, and the physico-chemical properties are the same at each of its points. A system is heterogeneous if it has several phases or if the single phase has different properties depending on the regions considered. A system can be open, closed, or isolated. Closed system, it can only exchange energy with the outside world. Open system, it can exchange matter and energy with the external environment. Isolated system, an isolated system cannot exchange either matter or energy with the outside world. Example: all bath heating coffee thermocalorimeter. Table 1. The different types of thermodynamic systems. Description of a thermodynamic system. System status. The thermodynamic state of a system is represented by macroscopic quantities relating to the microscopic state of the matter constituting the system. All macroscopic quantities, directly measurable or not, capable of describing the state of a system are called state quantities. State variables characterizing a physico-chemical system: temperature, pressure, volume, mass, concentration, density, number of moles and partial pressure. Thermal, P, V, T, or calorific, U, H, W, Q, S, variables or quantities. A state variable is always a scalar physical quantity. It is either extensive variables, they are proportional to the quantity of matter. They are additive and multiplicative exp, mass, volume. Intensive variables, they are independent of the quantity of matter exp, temperature, concentration, density. Ideal gases. The ideal gas is a thermodynamic model that allows us to describe the behavior of real gases at low pressure. This model assumes that the gas particles are sufficiently distant from each other to be able to neglect the electrostatic interactions which depend on the physico-chemical nature of the gas. Ideal gas hypothesis, kinetic theory. Atoms or molecules are likened to point masses. The molecules do not interact with each other. The pressure is due to the numerous impacts of the molecules on the walls of the enclosure. Equation of state of an ideal gas. The state variables of an ideal gas are: state of equilibrium. A system is said to be in equilibrium when the values of these state variables are the same at every point of the system and remain fixed as a function of time. We can distinguish different types of balance between the system and its environment. Thermal equilibrium. The temperature of the system does not change with time and has same values at all points of the system. T equals CSTE. Mechanical equilibrium. There are no unbalanced forces within the system or between the surroundings. The pressure in the system is same at all points and does not change with respect time. P equals CSTE. Chemical equilibrium. No chemical reaction takes place in the system and the chemical composition, which is same throughout the system, does not vary with time. NB. The initial state and the final state are equilibrium states. Possible transfers between the system and the external environment. The different types of transfer are the transfer of energy. A thermodynamic system can exchange mechanical work W and thermal quantity of heat Q energies with the external environment. Q and W are expressed in joules, J. Transfer of matter. Exchange of matter between the system and the outside world, through the wall. Matter can leave or enter the system. Transformations of the state of a system, operation, evolution. During a transformation, the state variables of the system vary to reach another equilibrium state. The transition from the equilibrium state, A, to the equilibrium state, B, generally takes place out of equilibrium. We then distinguish between reversible or ideal transformations. These are the infinitely slow transformations of a succession of equilibrium states. Irreversible, real transformations. These are rapid and brutal transformations out of equilibrium. The reversibility of a transformation requires that the system pass through an infinity of intermediate states that are little different from equilibrium states, quasi-static states. Spontaneous natural transformations are irreversible. They can only evolve in one direction. The different types of transformation. Transformation of an ideal gas. Isothermal transformation. It is carried out at constant temperature, T equals CSTE. Isochoric transformation. It is carried out at constant volume, V equals CSTE. Isobaric transformation. It is carried out at constant pressure, P equals CSTE. Adiabatic transformation. An adiabatic transformation is a transformation during which the system does not exchange heat with the external environment. Q equals 0, Q equals 0. This transformation is characterized by the Laplace equation. PV gamma equals CST gamma. Is the atomicity constant? It depends on the nature of the gas studied. Monatomic gases such as noble gases, last column of the periodic table. Physical state change transformation. Chemical transformations. These are chemical reactions such as esterification, combustion, etc. NB. These transformations can be carried out reversibly or irreversibly. Reminders of the ideal gas laws. A. Boyle-Mariotte law. It relates the pressure P and the volume V of an ideal gas at constant temperature. For an ideal gas, the product PV equals CST to T equals CST and nombre de mole constant. The transformation is called isothermal. B. Charles' law. A system can undergo a transformation at fixed pressure P equals CST V T equals CST. The transformation is called isobaric. C. Gay-Lussac law. A system can undergo a fixed volume transformation V equals CST P T equals CST. The transformation is called isochoric. D. Avogadro-Ampere law. At constant pressure and temperature, we have Vn equals CST. Mixture of ideal gases. Partial pressure, or a mixture of several gases. The partial pressure of one of the gases in the mixture is called the pressure that it would exert if it were the only one to occupy the entire volume. Dalton's law. A mixture of ideal gases is itself an ideal gas. The pressure of a gas mixture is equal to the sum of the partial pressures. Van der Waals equation of state. Real gas. In a real gas, the interactions between the molecules are no longer negligible and the molecules behave like spheres of radius r. The Van der Waals equation. A and B. Gas characteristic. N2V2. Internal pressure due to interaction forces between molecules. B. The covolume corresponding to the volumes of molecules that are not point-like. Noticed A. Open transformations. An open transformation is a transformation where the final state of the system is different from the initial state. B. Closed cycle of transformations. Series of transformations of the system which returns it to its initial state. State 1, 2, 3. 1. See notion of thermodynamic cycle. A thermodynamic cycle is a series of open transformations, or the system undergoes a series of transformations, which returns it to its initial state. Energy exchanges of a system. A system which undergoes thermomechanical transformations exchanges calorific, heat, and mechanical, work of pressure forces, energies with the external environment. Calorimetry is the measurement of heat transfer. It is carried out in chambers called calorimeters. A calorimeter is an insulated system, is a heat-insulated enclosure, a thermos bottle or calorimetric vase, thermally insulated from the external environment, which prevents heat exchange, carefully closed by a cap, which prevents material exchange. The calorimeter is used to measure the thermal properties of bodies, in particular their heat capacities or reaction energy, by measuring the temperature changes that occur there. Heat transfers take place inside the calorimetric container under atmospheric pressure. Heat or amount of heat it is characterized by a variation in the temperature of the system, T, or a change in the physical state of the matter of the system. Specific heats of bodies. It is the heat that is consumed or produced by a system when its temperature varies. The energy exchange which results from a temperature difference, T, between the system and the external environment. At constant pressure, Q equals mCpt equals CPT. M, G mass of the substance, C, cal K heat capacity, C, cal G dot K. Specific heat thermal capacity, specific heat, T, temperature difference, T equals final, T initial. Q equals N.C.Tn, number of moles. Noticed. For an isolated system adiabatic transformation, Chi equals 0. Calorimeter water value, the water equivalent, fictitious mass of water E, which absorbs part of the heat from the water heating the bodies inside the calorimeter and which induces heating of the internal walls of the calorimeter and these instruments, thermometer, stirrer. This water value has the same heat capacity that the bodies introduce into the calorimeter. Calorimetric measurement method by change of state. We call the heat which accompanies a change of physical state of a body to another state which takes place at constant temperature latent heat. Therefore, latent heat is heat which is consumed or produced by a system which changes phase. Its temperature remains constant. We distinguish three types of heat. Work of pressure forces. For an elementary displacement dx of the piston, the work of will be elementary, W equals Fex times dx equals Pex dot S. Dx S dot dx equals dV. Infinitesimal variation of the volume of the system, W equals Pex times dV, to respect the rule of signs, which means that the work received by the system is positive, W0. It is appropriate to add the sign, winky face, because during compression dV0, Fexed, force exerted by the external environment on the piston. For a finite transformation going from a state, 1, to a state, 2, W equals \int underscore, 2, caret, \frac, 2, 2, \delta W underscore, V underscore, 2, W equals \int underscore, V underscore, 1, caret, V underscore, 2, P underscore, extension, dV. Isochoric transformation, dV equals 0 \right arrow \delta W equals 0 and W equals 0. Reversible transformation. At each moment, P underscore exit equals P underscore int, tongue poking smiley, gas pressure, W equals \int underscore, V underscore, 1, caret, V underscore, 2, PdV. In the case of an ideal gas, P equals \frac, nRT, V, W equals \int underscore, V underscore, 1, caret, V underscore, 2, R nRT in \frac dV V. Isothermal reversible transformation. T underscore 1 equals T underscore 2 equals T equals constant V2 dVW equals nRT in V equals nRT, in V2 in V1. W nRT in V2 V1 P2 P1 V1 equals P2 V2 W equals nRT in P. Reversible isobaric transformation. P underscore 1 equals P underscore \frac 2 V. Tongue poking smiley equals W equals \int underscore V underscore 1 caret V underscore 2 PDV equals P \int underscore V underscore 1 caret V underscore 2 DVW equals P V underscore 2 V underscore 1. Irreversible transformation. V2. Pex dV. P underscore asterisk \PMP gas pressure in the case where P underscore extension equals CST W equals P underscore extension \int underscore V underscore 1 caret V underscore 2 dVW pext V2 V1. In the case of ideal gas, V equals \frac nRT P \right arrow W equals P underscore extension \frac nRT P underscore 2 \frac nRT P underscore 1. And for an isothermal transformation, P extension P2 W nRT P P1.